like I said, we should be able to answer these two questions without doing any calculations. So while I asked you to get textbooks out, it was not for this problem, okay? So keep them out, though, because we're going to need them for the next one. If you did the calculations, that's fine. You can still answer it from the calculations, but I want to show you how to answer them without doing any calculations. Whenever we're talking about temperature and delta G, what equation are we using?
Delta G equals delta H minus T delta S.
Delta G equals delta H minus T delta S. Going home to supper, right? And that is on your formula sheet, so you don't have to memorize it. You just have to know when to use it and how to use it. So let's think about this reaction in part A. What sign do you, let me back up. What do you think is happening to the disorder or the entropy during the course of this reaction? Is it increasing or decreasing?
Increasing.
Why do you say it's increasing?
Because when you increase temperature, it would go from like a liquid to gas, and a gas has more.
Just look at the reaction. You are way overthinking it. Just looking at the chemical equation, going from the reactions to the products, what's happening to the entropy? It is decreasing because we are going from a solid solid and gas to a solid. So the phases of matter is showing that it's becoming more ordered. Also, we have 1 and 3/2 particles on the left and then only one particle on the right. So it's also, we're decreasing the number of particles from the left to the right. So delta S is decreasing. What sign does delta S have when it's decreasing? Negative. And in this case, we're increasing temperature, and we're looking at how that affects delta G. Now let's talk about delta H. We did talk about this back in Unit 3, but let's review it. You should know from first year chem, what type of reaction is that? That is a synthesis reaction. Synthesis reactions are typically, almost always, exothermic. Because when you bring them together, it releases energy. So synthesis reactions are typically exothermic. If this reaction's exothermic, what sign does it have? Negative. And if you don't believe me that it's exothermic, that's where you could do the math to prove it, but it's exothermic, okay? So we have the same sign for delta H and delta S. Remember that chart we made last class? For those of you who were here, we made that nice little chart that showed what happens to delta G when delta G is... What sign does delta G have when it's favorable? Negative. So we kind of wrote it all out when depending upon the signs of delta H and delta S, delta G is negative under certain conditions, okay? So here, if we increase temperature, what happens to our delta G? It will increase. You could also say it becomes what? Less favorable. What sign will delta G eventually have? Positive.
Do you need to know what the change in entropy is? Because if you have T change in entropy, then that would tell you if it's going to increase or decrease. Because you know that the change in entropy is negative, so that means...
Well, yes, I understand that, but I'm going over all aspects of this reaction. So, as I was saying before I got interrupted, now I'm off my train of thought. Let's go back to what we were just saying so we can write it down. So, if we increase temperature, what happens to delta G? What happens to delta G? It increases or becomes more positive. And the reason I'm saying becomes more positive is because a lot of people think, for example, if I don't write this part down, but if I say negative 5,000 kilojoules per mole compared to negative 200 kilojoules per mole, Which one's bigger? Negative 200. Even though 200 is a smaller value than 5,000, it's negative. So this would be an increase of delta G. We're looking at like a number line. We've increased the value. We've increased delta G. Okay, so or it's become more positive, which decreases the favorability. So less favorable for this reaction. So this reaction would be more favorable if we have a lower temperature. And remember we did number 4 last class that showed you the, you could calculate the exact temperature at which it changes from being favorable to not favorable. Okay, and we'll do another one of those here in a little while. Okay? What about this next one? What equation do you think we're going to use? The same one. All right, let's look at all components of the equation, because the point of me going over this is to help you with something later. What sign do we think our delta S is going to be? Why do you say positive? There's 1 on the left and 2 on the right. We're increasing the number of particles. We don't have a phase change, so we're only looking at number of particles. Okay. So delta S should be, what did you say? Positive. What type of reaction is this? The first one was a synthesis reaction. What do you think this one is? Decomposition. The N2O4 is breaking down into 2 NO2 molecules. If synthesis reactions are typically exothermic, decomposition reactions are typically endothermic. You got to put energy in to break the molecule apart. Now, somebody in last class was like, but wait, I thought that when right, like when bonds break, they release energy, stuff like that. Remember, everything, you're always putting energy in and you're getting energy back out. All reactions, you put things in, you get stuff back out. You're looking at the difference. Yes, the net. Here, you put more energy in than you get out from the bonds forming of the NO2. You have to put more energy in to break the N2O4 bonds than you get back out when the NO2 bonds form, which is why it is endothermic. Okay, so what sign does delta H have? Positive. So we're going to increase temperature and look to see what happens to delta G. Okay, so it's like the opposite as letter A. The signs are the same, but they're both positive. What's going to happen to delta G as we increase temperature? It decreases, becomes more favorable, becomes more negative. All these different ways to say that. Hold on. Let me write this down. So delta G decreases or becomes more negative, so it's more favorable. So now on for number 6. Using the table of thermodynamic values, determine the normal boiling point of water. So we know what the boiling point of water should be. What should our answer be? Did you just tell me Fahrenheit? Ugh, get out of here. So this is science. Or 373 Kelvin, because we typically don't say degrees in front of Kelvin. You're still wrong. So yes, we know the boiling point of water to be 100 degrees Celsius, or 373 Kelvin. We're going to show that from the thermo side. Okay? We're going to show that from the thermodynamics aspect. Okay. Let's write out the chemical equation, I'm using quotations for that, for this process. Okay? We're boiling water. What's the formula for water? H2O. And it's liquid. Right? So that's like our chemical reaction, quote unquote. Right? Even though it's not a chemical change, it's a physical change. All right, so what type types of thermodynamic values do you think we're going to be calculating? Do you guys not know sign language? That's GH. Let's calculate delta H and
I already said delta S.
yeah, this is S, this is A. Oh, Z? Anyway, so you're going to calculate delta H and delta S for this process. And I'm not even going to label it as reaction, even though it's the overall. So it's delta H of the system, delta S of the system. What information do you think you need to use? What tool are you using? Your textbook, your appendix 4 in the textbook. So do me a favor, take a moment to calculate those two, and then we'll tune back in. So by now you should have calculated delta H and delta S. What did you get as your delta H? Is it positive or negative?
It's positive.
Positive. So remember, with our thermo stuff, we're always going to include a sign, even if it's positive. Okay? Because the sign means something. And that's kilojoules per mole, right? And what about our delta S? Now, let's think. Do our answers make sense? Do our signs make sense for the process? Let's look at the delta S. We're going from a liquid to a gas. Is that increasing entropy or decreasing entropy? It's increasing entropy, so delta S should be positive. To go from a liquid to a gas, do we have to put energy in or take energy out? We have to put energy in to make those particles move faster and boil, so delta H should be positive. So you should always be thinking, does my answer make sense? Okay? Now, what formula are we going to use next? What value are we solving for? Or what variable are we solving for? We're solving for T. So we know H, we know S. What are we going to plug in for G? Why? I did say that last class. Whenever it's asking like thermo and finding temperature, you're typically going to plug in a 0 for G when it's like the temperature at which something occurs. Yes. But why in this case? Why can't I just take the table and calculate delta G as well? Well, because for one, the table is for delta G at what temperature? What temperature? 25 degrees Celsius. Okay. Here, also, think about it this way. The question is, at what temperature will this boil? That was rhetorical. That was a rhetorical question. Water will boil at, we know, to be 100 degrees Celsius, or 373 Kelvin. We know water's going to boil at that temperature. What's happening when it's boiling is you actually have an equilibrium of the liquid and gas particles in that solution, which is why I wrote the reaction with an equilibrium arrow. Okay? We're basically trying to ask, like, at what temperature will this be at equilibrium? So then we can decide if we need to go greater than or less than temperature to drive the reaction to the right. And delta G at equilibrium has a value of 0. Okay? So we're going to plug in a 0 for delta G. Delta H we calculated to be positive 44 minus T, what? Yeah, we got to worry about our unit mismatch. Yes, we have to have the... So which one do you want to convert? Yeah, I want to convert the delta S because I've already written down the delta H value. So this in kilojoules per Kelvin mole would be what? Positive 0.119 kilojoules per Kelvin mole. Does it matter which one you convert? No, as long as you get to the same unit. Okay? So T times positive 0.119. Now you're just doing algebra to solve for T. We know it should be right around 373 Kelvin, right? Because we know what the boiling point of water is. Well, if this were a question that you didn't know the boiling point of already, then yeah. What'd you get? 370? So this is right around 100 degrees Celsius, right? I mean, it's a little bit off because we're using these table values, and I don't know how accurate they are. But yeah, it's right around 370. So now, at what do we need to increase the temperature to make this more favorable, or decrease the temperature to make it more favorable? Why do you say increase?
Oh, because it's a positive minus a positive. So if the
Okay, that's the correct answer. Why do you think we should increase? And your answer is not wrong. Let me rephrase that. Not necessarily the correct answer. That's what I'm getting at. A lot of you are probably thinking, oh, I'm boiling. I know I need to increase the energy, so I need to increase the temperature. Yes, but the reason why, the actual explanation why has to do with this thermo stuff, and that's what he was saying. Where, since it's positive, positive, this term needs to become larger. We need to increase this term to make delta G decrease. Because if it's at 0, we need to make this bigger to make this a negative. Okay? So therefore, any temp greater than 370K will make the process favorable. And that ends up driving this reaction up here to the right. Because remember, when it's at delta G, it's at equilibrium. It's kind of like in stasis there. Okay? All right. Number 7. You ready? Okay. I mean, I don't care. All right, number 7. The delta G for the reaction N2O4 going to 2NO2 was determined earlier. Actually, your packet gives you the delta G. I forgot that I had changed around your packet. I had eliminated the problem where we actually calculated it, and I didn't update my flip chart. So what is the delta G given to you? All right, positive 6.00 kilojoules per mole. Cool? Alrighty. So we want to calculate the K for the reaction at 25 degrees Celsius. Delta G and K. Hey, can you do me a favor? Look at the formula sheet. See if there's a formula on there that has delta G and K.
let's just derive it. Here's a good idea.
I don't want to derive it.
That's not the word.
Well, if you notice, the formula sheet is divided into sections, and it's labeled.
Just say no. Just say no.
All right, so we keep that formula sheet. You're gonna be using it again. So, guys, we do have this formula, and it is on your formula sheet. So therefore, you may very well have to do a calculation with it on the AP exam. You definitely will have to do a calculation with it on my unit test. All right. I call that the rat-link equation. Yeah, RT natural log of K. So actually, let's go over that. Now, I told you to keep it out. Why'd you put it away? All right, R. So there are 3 R values on the formula sheet. Why don't you give me all 3 of them?
And include units, because that's important.
8.314 joules, moles, -1, and Kelvin per
Okay, sure. I'm just going to write it like that. Okay. What's the next one?
0.08206 liters per atm mole per over mole temperature.
And what is the third one?
62.36 liters torr over mole per Kelvin.
All right. So we have these 3 R values. Liter atmosphere or liter torr. Okay, we have these 3 R values. In my years of teaching AP Chem, kids have shown me that they know what formula to use. Oftentimes we'll use the correct formula, but we won't use the correct R value. So let's talk through how we know which R value we're supposed to use. What do you notice about our second 2 R values? They both have a pressure in its units. For all 3 of them, the bottom is mole time Kelvin, right? But for the second 2, we have volume and pressure in them. Okay, we have liters and atmospheres or liters and torrs. In what types of calculations do you deal with volume and pressure?
Ideal gas.
Yeah, the ideal gas law. Are we doing the ideal gas law? No. No. All right. Also, what types of what unit is delta G typically in? Kilojoules per mole, right? Kilojoules per mole. Which one of these R's can we use for kilojoules per mole? The one that has joules. This one. So we're not going to use these 2 with this type of formula. So that is a big mistake people make, is they'll use the correct formula, but they'll plug in the wrong R. Okay? And even though I don't grade units in your problem, I'm not one of the physics teachers. Okay? I don't check your units or anything like that. And the AP exam doesn't either. They're not going to be looking for units within your work. This is where writing down your units, or at least making note of them, will help you along the way so that you know that you need to convert things properly and use the correct R value. Okay? All right, so now we're ready to plug things in. Also, notice that our R value has units of joules per Kelvin mole, but our delta G is kilojoules per Kelvin mole. So we have to convert. We either have to convert the R to kilojoules per Kelvin mole or convert the delta G to joules per mole. Does it matter which one? Nope. You want to calculate the delta G? So do I. What's the delta G in joules per mole? Yep, 6,000. Equals, and then negative, we're just going to plug this in. What is our temperature?
25.
With the proper units?
No.
298 Kelvin. And then times natural log of K. Something I did not know that I was going to have to teach. You have to isolate the natural log of K before you can do E to it. Okay? I have seen issues with that in the past, so I'm just pointing that out. Make sure you're doing your math properly. You cannot do E to both sides yet. You're going to have to isolate natural log of K first, and then do E to both sides. So go ahead and solve for natural log of K. You're just going to be dividing. This is all algebra. We've been doing algebra since like middle school, right? What did you get as your natural log of K? Negative 2 point. Negative 2.42
It's gonna be like 1.
is natural log of K. And now how do I get rid of that natural log? E to both sides. And that cancels out the natural log. What do you get? .0888. All right, now a few things I want to point out. Based off of the delta G, which side of the reaction is favored? Why are you saying the reactants? Because delta G is positive, and a negative delta G means that the reaction is favored in the forward direction, so therefore the products are favored. So when delta G is positive, that means the reverse reaction is favored, or the reactant side, right? Think back to Unit 5. What does our K tell us about which side of the reaction is favored? The reactants are favored. Why? Because K is less than 1. So let's think about this. When delta G is negative, what will the K be? Greater than 1. When delta G is positive, what will the K be? Less than 1. Now the difference here is that K isn't going to change. Delta G will change until the reaction reaches equilibrium. At equilibrium, K will be, at equilibrium, delta G will be 0. Delta G kind of tells you the direction the reaction will proceed in order to reach equilibrium. Okay. So it's delta G kind of is telling us that like Q versus K shift type stuff, right? Okay. Ready to do B? All right, so we're going to be calculating delta G for the reaction at the partial pressure, and then blah, 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 blah. I don't want to read it all out loud to you. What do you notice about this delta G right there that I just highlighted? It doesn't have what? That's just a typo, right? No, it was deliberately left off. Because this is non-standard conditions. All right, so pull back out that formula sheet, which I didn't tell you to put away. And find this formula on the formula sheet. Find that on the formula sheet. Your grade depends on it. You better find it. Is it on your formula sheet?
No.
It's not on your formula sheet. So what does that mean?
Wait, what?
You are not responsible for it.
Clutch.
Okay? That Facebook group that I'm part of, there's a lot of questions constantly about like, oh, stop. There's a lot of questions about like, hey, is it required to do this? Is it required to like deal with delta G at non-standard conditions? Things like that. And while there's merit in it and it's part of thermodynamics, it's not part of College Board. It's not part of the AP exam. So why waste the time and the brain power learning it if you're not going to need it? Okay? So I'm trying to do better about only going over the things that are absolutely vital. Okay? Yep, we're just going to move on to number 8. My arrows are missing in the reaction on number 8. Yours are fine, but it was just mine that isn't. All right. So consider the reaction 2Cl2 plus 2H2O going to 4HCl plus O2. The concentration, equilibrium constant, Kc. Guys, stop talking. For this reaction is 1.12 times 10 to the negative 3 at 750 K. Would you expect this value to increase or decrease at 300 K? Explain your answer using words, no calculations yet. What other piece of information do you think you need to properly answer this question? And don't say the right answer. What? No.
I don't think we need it.
You don't think you need anything else? You can answer it as is.
Oh, the value of AC equals delta H.
Do you need the actual delta H, or do you just need to know the sign of delta H? You just need the sign of delta H. You need to know if it's an endothermic or exothermic process. Okay? What type of problem? Whose principle is this? Le Chatelier's principle. That was a very loaded question because we've only talked about one principle. This is a Le Chatelier's principle question. Technically, if given the sign of delta H, you should be able to answer this question based off of what you did in Unit 5. Okay? So this is Le Chatelier's principle question looking at, like, for changing the amount of temperature or the amount of heat, which way is the reaction shifting. So you need to know the delta H, or at least the sign of it. Okay? So I'm going to tell you that delta H is a positive value. Okay. If delta H is positive, that means it's what type of reaction? It's an endothermic reaction. So, what side of the reaction are you going to put heat on? The left. All right, so what am I doing with the temperature? I'm looking at, I know the temperature, I know the K at a high temperature, and then I'm looking at the K at a lower temperature. So yes, temperature is decreasing. So as temperature is decreasing, which direction is this reaction shifting?
Oh, it's decreasing.
It's one of those ways. I've heard the correct answer, not from over here. Which side? Which way are we shifting? To the left. Do you understand why? We're removing heat from the reactant side, so we're going to shift left. So as temperature decreases, reaction shifts left. And when the reaction shifts left as a result of a temperature change, what happens to K? So K decreases. Okay? So therefore, the K at 300 Kelvin is smaller or less than the K at 750 Kelvin. Do you understand that? In a little bit, we're going to do some calculations, but let's predict the delta G stuff. We know that the K, the equilibrium constant at 750 Kelvin, is 1.12 times 10 to the negative 3. What do we predict the sign of delta G to be at 750 K? Positive. Because the K equilibrium constant is less than 1. So the delta G should be positive at 750 Kelvin. If K is smaller at 300 Kelvin, how would you compare the delta G at 750 Kelvin? So delta G at 750 compared to delta G at 300. How would you compare their... Yes, exactly. Delta G at 300 should be greater than delta G at 750 because at decreasing temperature is shifting it more and more to the left, making it less favorable. becoming less favorable at lower temperatures. Okay, and we're going to use that prediction in a little bit when we do the calculations to make sure it matches up with our prediction. Okay, again, constantly asking yourself, does my answer make sense? Does my sign make sense? These are things that will help you with these calculations. Okay? Can you see all right? Okay. That's why I'm leaning back like this, because of you guys. Ready to do B? I need to fix this because all my little arrows are gone. All right, so consider the reaction. It's the same reaction. So calculate delta H and delta S for the reaction from the table of thermodynamic values in your text. What equation are you using? Big Mama. You're calculating delta H and delta S from the thermodynamic table. Okay. So I'm going to give you guys a few minutes to do that. So for the delta H, let me set it up because last class we did have some students have some issues with this. All right. The one thing I wanted to point out here is to put like these big brackets around the reactants and the product sides. Some people last class were not in parentheses or bracketing the entire reactant side, and they weren't distributing their negative sign. And they were doing some algebra problems wrong. They were having some algebraic issues. Okay? It was not good. I agree. Where did I get all these values from? The table in the textbook. Now remember, for these values, states of matter matter. Okay? Make sure you're pulling the correct one. This is water in the gas state, not the liquid state. It's HCl in the gas state, not the aqueous state. Okay? So make sure you're checking the state of matter as well. All right, so what do you get as your delta H? Thank you for giving that to me with the appropriate sign. And then for delta S, and we were saying this when we were paused, remember every substance has an entropy value, regardless of what its H value is, or G. Remember, elements and diatomics in their natural standard state, their delta G and delta H are 0, but S, everything has one. What do you get as your delta S? And what are the units here? Joules per Kelvin mole. And that's all we have to do for B. It was just what's the delta H and what's the delta S. Cool? Cool? Can we do C? All right, so for C, we're using the values obtained in B, calculate delta G for the reaction at 300 Kelvin and at 750 Kelvin. What equation are we going to use that uses the stuff we calculated in B? The going home to supper equation. Is there anything else you could use to find the delta G? Maybe not what you've used in B, but maybe something from A? You could use the Ratlink equation, but that would only give you delta G at 750 Kelvin, because that's the only one that we have the equilibrium constant for. But I'm going to use the going home to supper equation. So I'm going to find delta G at 300 Kelvin and delta G at 750 Kelvin. Okay. These two equations are going to be almost identical. What's going to be different? The temperature. Before we can plug the delta H and delta H, before we can plug the delta H and delta S into the equations, what do we need to do? Get them both to the same unit. Doesn't matter which one you convert. Nope, I like converting delta S. So my delta H is still going to be positive 116. minus 300 Kelvin. What's going to be my delta S in kilojoules per Kelvin mole? 0.129. And then this one will be same thing, but 750 Kelvin instead. Now, before we give the answers, what did we predict in part A to be the larger value? The 300 Kelvin, remember? Back here we talked about it because delta G at 300 at the lower temperature, it's less favorable. A larger delta G means it's less favorable. The smaller or the more positive delta G is less favorable. Okay, so we predicted delta G at 300 to be a larger value. So if you don't get something that's bigger or larger, more positive, you've done something wrong. Maybe it's as simple as you forgot to convert both your one of your H or S to the same unit. Or maybe you use temperature in Celsius if it was given to you in Celsius, something like that. Or maybe you accidentally added here instead of subtracting. Okay, so just try to figure out what your mistake is, but that should be a red flag that you've done something wrong based on your prediction. What do you get as your delta G at 300? You guys did so well with the delta. There we go. Positive 77.3 kilojoules per mole. And what about at 750? Cool. No. I would not take points off if you don't put the positive down.
Yes, you would.
It depends on the way that the question is worded. If it specifically says to include a sign with your answer, then yes, I would take off points if you did not include a positive. But I'm fairly positive, no pun intended, that on the AP exam, if you're solving for delta G and it just said what's delta G, include units, or like what's delta G in kilojoules per mole, and it was a positive value and you did not write a positive, I'm fairly positive you will not get points off. I will confirm that though. Okay, but I will. Well, it's not really a group chat, it's just a group. But I will try to remember to ask that question or see if there's. I'm sure that question's already been asked, and I will try to find it in an earlier thread for you guys, okay? Ready to do letter D? All right. So now, calculate Kc for the reaction at 300 Kelvin, and then compare it to your value. Compare your value with your prediction in A. So we're calculating K. What equation are we using? RATLink. What delta G value are we going to use? The 77.3 value. And that is kilojoules per mole. So what do we need to make sure R is in? But that's joules. So we need to convert it to kilojoules is what I'm getting at. So you got to convert that R to kilojoules. So you can just take 8.314 times 10 to the negative 3. And that's going to be kilojoules per Kelvin mole. What's our T? Yes, 300 Kelvin, natural log of K. So isolate natural log of K, and then we'll solve for it. What do you get as your natural log of K? Negative 30.99. It should be, you forgot the negative in front of, it's minus RT. Or it's negative RT, ln K. Alright, so you should get negative 30.99. And then how do we get rid of the natural log? E both sides. E to the this, e to the this. Now before we solve for it, what did we predict that the K for 300 Kelvin would be in comparison to the K for 750? We predict it to be smaller. Kc at 300 should be smaller than 1.12 times 10 to the negative 3. That was our prediction. Okay. So now let's do the math to show that our prediction makes sense. What do you get as your K? Negative 14? Is that what you said? Is that smaller than 1.12 times 10 to the negative 3? Yes, it is. Our prediction is good. Cool? Makes sense?